Thank you very much for coming. My name is Yue Sun. I'm a PhD student at the University of Tokyo. Today, I'm going to present my research on meta-learning in decentralized neural networks towards more general AI. I have been obsessed with working on AI because I truly believe it's one of the most important things we can work on and one of the most powerful technologies we ever invented. Deep learning is constantly changing our world, both in industry and scientific discovery, and we will see it continues to act as a technical innovator for the foreseeable future. One of the questions I have been asking is the limitation of deep neural networks in out-of-distribution generalization. We typically train neural networks using data from a single distribution and apply the model to unseen data from the same distribution. However, real world is not like this, often with uncertainty in diverse data distribution, leading to poor model performance on unseen data. The challenge is to develop neural networks with improved generalization capabilities beyond the training distribution. To achieve this goal, training on all real-world data seems intractable. Instead, we can consider the meta-learning scenarios, where to tackle a new task, we aim to select and combine knowledge learned by different individual models. It allows the agent to extract common, stable, and reusable information, such as the learned representations and updated model parameters from past experience and task, thus without need of large-scale training. My study of meta-learning in decentralized neural networks is inspired by Bass' global workspace theory from the 1980s. According to this theory, the human brain solves the problem through cooperation and competition among neural network models in a shared space, which is commonly referred to as the working memory. One aspect of this theory is the ability to perform fast and precise habitual actions through unconscious, specialized processors. On the other hand, controlled cognitive processing can also occur in the global workspace through selection and reuse of learned specialized processors. I will be presenting today on 3 approaches to improving neural network generalization through the knowledge transfer. I will discuss how Replica neural networks, hierarchical neural networks, and multimodal neural networks extract reusable information from previous experience and tasks to enhance generalization capabilities. These approaches tackle the knowledge transfer problem in different ways and are crucial to build more generalizable neural networks. First, the replica neural networks are models with similar architecture and functions in multi-modal settings. The concept behind these neural networks is that they can improve performance on unseen tasks through knowledge sharing and social learning among these different agents. This approach differs from the large foundation models that rely solely on the large-scale training to improve the performance. As I mentioned earlier, a key shortcoming of the modern deep neural networks is that they usually show the good in-distribution performance, but struggle in the out-of-distribution, the OD settings, such as a distributional shift between the train and test dataset. Now consider a train dataset DS and a test dataset DT that share the same support of the input and output space. Their inputs have domain discrepancy with specific styles due to factors like data collection environments. For example, in the digital image classification task, some data domains have more complex backgrounds with lots of irrelevant information. The challenge lies in the tackling the test task based on information obtained from the training dataset. Intuitively, by distilling the reusable knowledge representations and discarding irrelevant information from a trained model on the source domain, we can effectively train a model on the target domain using the relevant representation extracted. This leads to more efficient learning in the target domain. To illustrate this point, consider multiple agents train separate models using samples with different styles. maybe due to their data collection environments. Then the goal is to solve a novel task leveraging the reusable information from this model's local task. We proposed a new multi-source domain adaptation method that disentangles the domain-relevant stationary features from these different local tasks and models of agents to improve the global model performance in novel tasks. Since directly using the learned data representations from the different tasks is challenging due to the noise and the distractions in the training data, our proposed method aims to effectively reuse the information from different domain tasks by distilling the reusable information from different domains. We performed the evaluation in 2 image classification datasets and text sentiment classification datasets for different domain adaptation tasks. Especially for each dataset, we considered one domain as the target task and train a model based on the remaining domains to tackle the selected target task. This graph shows the knowledge transfer loss in the learning process. Initially, the training loss was high due to the limited shared information among these agents. As learning progressed, the efficacy of knowledge sharing improved, as shown by the decreasing scores. That's because there are more reshareable, reusable information learned by the different agents. This decrease will continue until a certain convergence point. Compared to the baseline methods, our framework enables a late convergence phenomenon of learning, leading to improved reusability of past knowledge for better generalization to new domains. As demonstrated in this table, our method outperforms other methods in transfer learning for domain shift problems across different tasks. I also present the T-SNE visualization of the learned representation distributions, and the results show that transferring knowledge leads to improved representation quality for classification tasks. Hierarchical neural networks consists of multiple neural networks organized in a hierarchical structure. A meta model learns optimized policy to facilitate learning in these networks. At each time step, the learning process in a specific state represented by a module, and the decision maker can choose any available action. Each action changes the state of the module by combining it with another selected module, and result in a corresponding reward based on the new module's performance. The objective is to maximize the cumulative reward along the entire process route, starting from initialized point and ending with the desired model performance. Hierarchical neural networks take advantage of faster inner learning loops for obtaining task-specific knowledge and a slow outer learning loop for optimizing the inner loop learning policy, allowing for efficient reuse of the obtained task-specific knowledge. We tackle the challenge of training models on non-ID data, where each model is trained using data with a specific class distribution from the same dataset. It's crucial to have reliable incremental measures of progress and improvement in hierarchical neural networks to ensure the successful knowledge transfer. In this graph, each cluster represents the compressed weights of the multiple modules that share similar training data classes. The star symbol represents the initial state of the hierarchical system, and the direction of the system's movements depends on the selected module. For example, the star can move towards the direction of the orange cluster, or it can move to the red cluster, depending on the different sections of the action. We employ the deep Q learning, a type of reinforcement learning for the slow learning outer loop. This combination of meta learning and reinforcement learning aims to maximize the system performance. The system has no pure knowledge of each module's class distribution, and the Q learning algorithms predict the action with the highest expected rewards based on observe the states of different modules in the systems to maximize the long-term reward. This graph illustrates the episodic rewards with the progress of training 100-module hierarchical neural networks in the MNIST datasets and the fashion MNIST datasets. The systems learns to maximize the episodic rewards during training, which facilitated the learning process for new tasks. In this graph, I compare the convergence time between the proposed method and the baseline method, highlighting the influence of data distribution uncertainty on performance. The results show that leveraging an outer loop learning process to learn an optimized knowledge transfer policy can significantly reduce the convergence time by almost 50% when training on the non-ID data. The knowledge transfer problems we discussed so far are limited to a single modality. However, intelligent systems usually build models of the world with different modalities. It's crucial to transfer knowledge across different modalities as well. For that reason, the last point I want to discuss is about cross-modal knowledge transfer. One example of the cross-modal learning is the visual question answering task, which aims to produce a correct answer given the pair of the image and the question. Training a VQA model on the entire data distribution is challenging because it may not be feasible in real-world scenarios. In such cases, multiple agents that represent different perspectives of the data collaborate with each other to improve the generality of the model for unseen situations. Transferring and aggregating the knowledge of these agents is crucial to achieve this. In our approach, we transfer the knowledge between modalities using self-supervised learning. By this, we can obtain reusable cross-modal representations without using any training labels. The alignment of representations is achieved by encouraging the similarity between relevant input modality samples and discouraging similarity between the irrelevant ones through a contrastive loop. This approach also retains the model interpretability by producing the attention maps, which highlights the important objects in the input samples. We evaluated the method effectiveness on 7 state-of-the-art VQA models. The results showed that the self-supervised learning-based approach is model agnostic, can be effectively applied to the different VQA models. The VQA models trained with cross-modal knowledge transfer performs well on general content, sometimes can struggle with details though. An example is shown to demonstrate this. It shows that there may be a trade-off between the model performance and the usage of collaboration learning between these different agents. In conclusion, the ability of neural networks to generalize to out-of-distribution data is a well-known limitation. To overcome this limitation, the benefits of knowledge sharing and social learning among neural network models in unseen tasks are highlighted in this presentation. A network of interconnected neural network models with a similar architecture can be leveraged to share knowledge, and hierarchical neural networks with a meta model can be used to optimize the transfer learning policy. Furthermore, the self-supervised learning can be used to transfer knowledge between the different modalities without the need for labels. These approaches can help to improve the overall performance of neural network models and to tackle the limitations of out-of-distribution generalization problem. That concludes my presentation. Thank you for your attention.